The main running example that I will give here in this talk, or will talk about in this presentation, is the one that you can see here on the slide. It's just a small demo application where we have a player character which has a move and attack animation, and we have a background with a scrolling parallax animation. So first I will give a small overview of some of the concepts within PaSe. So as I said, we're going to be creating animations in a compositional way, so we need some kind of basic unit of animation. We have, this is what I call atomic animation, which are the indivisible units which we'll be using to compose animations together. And so these atomic animations, they just state in some form how the application state should change over a certain period of time. We will see some examples of this later. So, and then we have two units of composition, where we have parallel composition, which states that, or expresses that two animations should be starting at the same moment in time. And we have sequential composition, where we express that one animation should start, and then afterwards another animation should start playing. And so this is also where the name comes from, the first two characters of parallel and sequential. So the first atomic animation, an example of an animation that I want to look at, is the linear 2 animation. So linear 2 will takes three inputs, the property and the state that we want to change. So in this case, we have the player character, the x value of the player character, which we want to move to a certain target value over a period of 1 second. And so this is expressed in the, so I will be showing the animations in a sort of timeline to show you, to this sort of quick way what the animation should do. And then this is the code counterpart where we, so DSL is embedded with, this is the actual Haskell code that you can use to create this animation. So as I said, we have the three properties, well, the three inputs. The first one is the property, the player.x value. We have the duration, 1 second, and the target value, 300. And so the animation before, the move x animation, was just the character sliding over the screen, but that's not exactly what we want. We want to have our character look like he's actually moving. And so if we describe in a timeline what we want to have the move x in parallel with some other animation which changes the texture of the player. And we will define this animation later on, but the essential part here is that it is an example of a parallel animation. And I use, so the parallel function is a binary function, and I use the infix animation. So we have move x parallel move sheet. We also have the sequential composition, where we have the swing animation, and then afterwards, or first and afterwards, we have this -1 particle that appears on top of this line. And so this is an example of something that we could do within a sequential animation, where we say swing sequential -1. So now I want to look into some animation techniques, or more difficult or complex animations we can create using these basic concepts. And so the first is a frame-by-frame animation, where we have a series of textures that we want to display with some small delay in between them to create a frame-by-frame animation. And so in the timeline, we would describe it like this. We set the texture, and then we have a delay, and then continuously do this for each of the textures. And so the set and the delay animations are, again, examples of two different atomic animations, where the set just instantly changes the state, and delay just waits for a certain amount. So technically, the timeline should look more like this, because the set does its effect instantly, but clarity I will use more this. In code, we have the, you saw that we had a series of boxes that should be played after one another. And so when we convert this into code, we just have a sequence of atomic animations that are combined sequentially. So they will play one after the other. And of course, we can, since the DSL is embedded within Haskell, we can use its code reuse facilities to create a function out of this, so we can reuse this frame-by-frame function if we want to use it for other frame-by-frame animations with other textures or on other properties in the state. Okay, so next I will talk about how to create the scrolling background. So I will do this in 2 steps. So first I will talk about the infinitely scrolling background, and then next I will talk about the parallax effect. So square, which kind of represents the viewport of the application, and then we see the actual texture of the background is larger than this viewport. And we will also be having 2 instances of this background next to one another. And so what will happen in this scrolling background animation is that we will move everything to the left at the same time. And then afterwards we will put this this first background section back to the right again. And so in this way we can, once we swap, consider 1 and 2, we can repeat the same animation continuously to get a background that scrolls infinitely. And so in a timeline, we can describe it like this, where we have the moving of the backgrounds. In parallel, we have, and then the resetting and the flipping, which technically takes instant amount of time. So there is a continuous movement of the backgrounds one after the other. And so we have kind of the same pattern as we saw before, where we converted timelines into code. We have the section of the moving of the backgrounds, which is composed in parallel. Then we have the are composed with the sequential function. We have the resetting of the background, and then the infinite scrolling is done by using recursion, where we swap the section 1 and 2 to have the flipping effect. So next up is the parallax effect. So this effect is basically where our background is separated into different layers, and the front layer moves faster than the back layer. So this also happens when we move our viewpoint in real life. If we move our head, for example, the objects that are closer to us, they move much faster compared to objects that are further away from us. If we represent this in a timeline, we reuse the same idea as before, scrolling backgrounds, but with different cycle times. Right? So the objects in the front will have a shorter cycle time, and than the objects in the back. I think this looks actually in code for this case, where we can reuse the function that we defined before, pass it different cycle times, and for each of the background sections, and compose everything in parallel. And then we have our parallax background. And so again, we can make a function out of this if we want to. So the last animation that I want to talk about is the hit stop, where so the swing animation of the character is, again, a simple frame-by-frame animation, as we saw before. So the hit stop effect is basically when we have our character here, which is actually hitting the slime, then there will be I don't know if you notice it by comparing them next to each other. So there is a longer delay here after this frame to sort of emphasize that the attack connected. And so the reason why I bring this animation up here is because it's an example of a conditional animation. So because we need to during our animation, we need to evaluate whether a certain condition is true, and then depending if it is true, we need to have a larger delay, and otherwise we need to use the short delay. And this kind of animation is not something that we can express using the parallel and sequential concepts. But PaSe is built with an open encoding, So we can add new constructs as we see fit. So we can add new control flow constructs, such as the if-then-else construct, which operates in the way that I described. It evaluates the condition and then will either execute the then branch or the else branch. And you might wonder, well, Haskell already has an if-then-else construct. Can't we reuse that one in our animations? And the answer is yes, you definitely can. But the thing is that you might not always want to. And the reason for that, it ties in with the next point that I want to talk about, which is the inspectability for DSLs. So what is inspectability? Inspectability is essentially the static analysis counterpart for domain-specific languages. So where we want to extract information from things expressed in our DSL, but actually running the animation or whatever it is that our DSL expresses. So examples in the use case of animations is we might want to extract the textures that our animation uses, or we might want to have calculate the duration of our animation, or see whether certain parallel or animations composed in parallel don't have any conflict, which means that they don't target the same property, which would be a conflict. And so, for example, in the demo application that I created, I used this ID to, instead of having to enumerate all the textures that my animations use, which would look something like this, I can analyze or inspect the DSL, the textures that are used inside my animations, extract them, and then load the textures into memory without having to enumerate everything myself. So how does this work? Well, the idea is that we basically gave a different interpretation to the constructors which are present in our DSL. So we have, so in this example, we have the frame-by-frame example that I put at the top here. We have the set delay, and hidden from the view is not explicitly given in the slides is the sequential composition of each of the boxes. And so instead of giving it the usual interpretation that the DSL would give it for running the animation, we give it a different interpretation. For example, to find the textures. Right, so when you want to extract the textures, we interpret the set constructor by extracting the texture that is inside in a singleton list. We don't extract anything or the empty list for the delay constructor, and then the interpretation for the sequential composition will be concatenating all the lists, and as an end result, we get all our textures. And something similar for the delay constructor, where we have have our duration inside our constructor, and we say, or we extract the duration, we extract the zero duration for the set, and then add everything up for the sequential composition. And this brings me back to the earlier point with the if-then-else construction. So if we would want to reuse the if-then-else Haskell construction, we have to add, or one way of doing this is by adding this complex composition operator, which is the monadic composition. And so in this monadic composition, we have an animation returning a result of A, and then in the second part of that animation is a function, so where we have to input the value A to actually know what the second part of the animation is. And the problem here with respect to inspectability is that this function is not inspectable because well, we don't know what's going on inside this function, and if we would want to inspect it, we might have to, for example, if the A is infinite, is an infinite amount of values, then we can't inspect all the possible continuations. But even if it is bounded, it might be computationally very wasteful to inspect all the possible continuations if, for example, this was only used for an if-then-else construction with 2 branches. And so this monadic composition, it's possible to use it, but if you care about inspecting your DSL, it's not always a useful thing to have. And so there is always this kind of trade-off between expressivity and inspectability. Right, so expressivity is in the sense of, for example, the monadic composition is very expressive. We can use it to create a lot of expressive other things, such as we can reuse it to have the conditional animations. But it's difficult with respect to inspectability. But kind of PaSe sort of, because of its use of an open encoding where we can add or control flow constructs as we see fit, right? So we can add our own if then else construct, provided that we also know how to want compatibility features for it. So in conclusion, I gave you some examples of how to express animations in a compositional manner. By giving these examples of animations, I gave you a sort of introduction to the PaSe DSL and also gave you a taster of the trade-off in inspectability and expressivity of DSLs. The paper talks about the same topics, but goes a bit more detail on the actual DSL design using the MTL or finally tagless encoding, and also a more detailed exposition of the trade-off that I mentioned between expressivity and inspectability. So here you can find the relevant links for the paper details. Thanks for your attention, and I'm happy to answer any questions.